In this video, we'll look at how to simulate I/O mapping using only the Robot Controller Simulation RCS, and how to switch signals within the simulation iiQWorks.Sim. We're working with a robot KR10R1102 that has a 2-finger gripper. Let's start by looking at the robot program. The most important part is in the config.dat file. Here, we've declared a global signal called colorNum. This is an integer variable that's linked to digital inputs 120 to 135. That means we're using 16 digital inputs to represent a single integer value. Depending on the value of colorNum, the robot will jump to different cases in a switch case statement inside the main routine. At the beginning of the program, there's a loop that waits for a rising edge on input 19. Once that signal is received, the robot checks the value of colorNum and jumps to the corresponding case. If colorNum is 10, the robot picks the blue cube. If it's 20, it picks the yellow one. If it's 30, it picks the red cube. And for any other value, it picks the green cube. Now let's look at how the inputs are connected in the simulation. To simulate input signals for the robot, we've created a custom component called IntegerDummy. This component allows you to enter a decimal value, which is automatically converted into a binary signal. That binary signal is then mapped to the robot's digital inputs. Let's have a short look at how you can build this component. First, we need to activate the modeling add-on. To do this, go to the File tab, then open Options and navigate to the Add-ons section. Make sure the iiQWorks.Sim modeling add-on is activated. You might need to restart iiQWorks.Sim after enabling it. Once the add-on is active, go to the Modeling tab and click on New Component. We'll name this component IntegerDummy. To make it visible in the 3D environment, let's add a simple geometry. In this case, we'll create a cylinder. The size doesn't matter, it's just for visual reference. Now let's add the properties we need. In the Properties section, we'll create 2 integer properties. Start input value. This defines the starting input number for mapping. Integer value. This is the value we want to send to the robot. You can set the integer value to any number for testing, for example, 26. To make the component easier to recognize, we'll change its material color to blue. And that's it. Now that we've created the IntegerDummy component, we need to add some behaviors to make it functional. First, go to the Behaviors tab of the component. Here, we'll add a robot interface. This will allow us to send signals from the dummy component to the robot. Click on Add Behavior, then choose One-to-One Interface. We'll name it simply Robot Interface. Next, we'll add a Python script to handle the logic. In the Behaviors tab, select Python script. When you add the script, it should automatically open in the editor. If it doesn't, you can open it manually by selecting the script and clicking Open in Editor in the Properties panel. Now we'll write a small piece of code that reads the integer value from the component and converts it into binary signals. These signals will be sent to the robot via the robot interface. When the simulation starts, the script checks if the dummy is connected to a robot. If it is, it reads the integer value from the component and splits it into 16 bits. Each bit is then sent to the robot's digital inputs, starting from the input number defined in the Start Input property. The script also listens for changes in the integer value or the start input and updates the robot inputs automatically. This way, you can control the robot's behavior using a single integer value instead of setting each input manually. You can pause the video and copy this code line by line, or you can write your own Python script that does the job. Once you're done, you can compile the script and use it in your simulation. Let's go to the Interfaces tab and connect the robot interface of the IntegerDummy to the robot. Once connected, we define the starting input number. Earlier, we saw that the colorNum variable is linked to input starting at 120. So here, we enter 120 as the starting input. This allows us to write values to the colorNum variable directly from the simulation. Next, we need to trigger the robot program. For that, we also need to simulate input 119, which is used to start the execution. To do this, we navigate to the Modeling tab, select the IntegerDummy, and in the Behaviors drop-down menu add a new signal. This time, it's a Boolean signal. Let's name it out 119. Now go to the Connect Signals button and connect this new signal to input 119 of the robot. You can simply tap the signal and enter the number 119. This setup allows us to simulate both the value of ColorNum and the start signal, enabling full control of the robot's behavior in the virtual environment. In the previous step, we simulated input signals to control the robot. Now, let's look at how to monitor the output signals to verify the robot's behavior. In the robot program, we're not only reacting to inputs, we're also setting outputs. Specifically, we're using outputs 103, 104, 105, and 106. You can simulate these outputs by creating Boolean signals in your IntegerDummy component and connecting them to the robot's outputs. But there's an easier way to monitor them. Open the monitoring window in iiQWorks.Sim and add the following signal names: out 103, out 104, out 105, and out 106. These are the variables that will reflect the robot's output state. Depending on which case the robot jumps into, the corresponding output will be set to true. Once the robot finishes its task, the output will return to false. Let's run the simulation. In the component properties, we enter the value 26. This value doesn't match any of the defined cases for blue, yellow, or red cubes. So the robot should pick the green cube. Now, when we set input 119 to true, the robot starts executing the program. Watch the monitoring window to see which output becomes active. This confirms that the robot logic is working correctly and that the signal mapping behaves as expected. Now let's validate the robot behavior by running the simulation and observing the signal flow. First, we make the robot signals component transparent so we can better see the signal activity. You'll notice that the robot is waiting for input 119 to become true. This input acts as the trigger to start the robot program. Once we set input 119 to true, the robot begins moving. You can see that output 106 becomes true, indicating that the robot is executing the green cube pick routine. After the task is completed, output 106 returns to false. Let's try another case. If we want the robot to pick the red cube, we enter the value 30 in the IntegerDummy component. The robot is now waiting again for input 119 to go from false to true, a rising edge. We first set input 119 to false, then back to true. This triggers the robot to execute the red cube pick routine. You'll see that output 105 becomes true during execution, and then returns to false once the task is done. We can repeat the same process for the yellow cube by entering 20, and for the blue cube by entering 10. Each time, the robot jumps into the correct case and sets the corresponding output signal to true. This confirms that the I/O mapping and signal logic are working correctly in the simulation iiQWorks.Sim running the Robot Controller Simulation RCS.
Thank you for joining us today. If you enjoyed this video, please like and subscribe the KUKA channel for more content. For practical training and workshops, visit the KUKA College. Stay tuned for more tutorials and insights.
Making automation easier.